This simulation of a satellite during a rocket launch illustrates a strict physical reality. Engineering environments are inherently chaotic. A central structure doesn't just experience one force. It absorbs thermal expansion, acoustic vibration, and axial g-forces all at the exact same time. When you translate that overlapping physical chaos into mathematics, you end up with highly entangled, coupled variables. The forces are inextricably linked together in a single system. On a chalkboard, that entangled system looks like this rational function, a dense polynomial divided by another polynomial. This represents all of those overlapping physical stresses locked into a single, non-trivial equation. Here is the primary roadblock in physical design. You cannot directly compute an integral for this coupled mass, and you certainly cannot manufacture a steel bracket to withstand an entangled multivariable equation. The solution requires breaking the system down. Before we can solve the calculus, we have to mathematically reverse engineer the structure itself. We do this using two highly specific tools: partial fraction decomposition and integration by parts. In academic settings, these are often treated as mere algebraic tricks to pass a test. In application, they are critical structural mechanisms used to isolate overlapping variables so that a system can actually be built. To see how calculus operates under the hood of the real world, we are going to map these decoupling tools directly to three domains: aerospace structural loads, electronic signal processing, and recursive software architecture. We start in aerospace engineering, looking specifically at the stress accumulating on a satellite central bus structure. The total mechanical stress acting on a single mounting bracket is a unified, chaotic load. Thermal expansion and acoustic vibration are violently pushing and pulling on the exact same bracket surface area simultaneously. Look at this 3D vector model of the bulkhead. The overlapping forces map precisely to this coupled accretion. The denominator contains both forces multiplying against each other, creating a system too complex to reinforce directly. We deploy partial fraction decomposition. This technique works strictly on proper fractions, meaning the degree of the polynomial on top is strictly less than the polynomial on the bottom. By factoring the denominator, we force the entangled system apart. The single complex fraction mathematically breaks into a sum of simpler, isolated components. The first extracted constant, A, represents the isolated thermal load. Because this variable is now isolated, an aerospace engineer designs the specific metallurgical response required to handle the heat, independently of the vibration data. The second constant, B, isolates the acoustic vibration. The structural forces are now decoupled. With the loads broken down into these independent point load fractions, the calculus becomes straightforward. These isolated fundamental fractions can now be trivially integrated into simple logarithmic functions. Partial fraction decomposition takes a coupled physical stress problem and physically snaps it into manageable, independent engineering constraints. This exact mathematical decoupling scales directly into electrical engineering, driving control systems and signal processing. Consider an RLC circuit, a resistor, inductor, and capacitor wired together. The way voltage flows through these three components over time creates a highly entangled electrical system. To evaluate how these circuits react to inputs, engineers run Laplace transforms. As shown in this schematic, the physical circuit converts into an abstract frequency model, outputting this dense polynomial transfer function in what engineers call the S-domain. In its current state, that S-domain function is mathematically unreadable. You cannot determine a voltage spike from a massive coupled polynomial. To make it readable, the electronics engineer applies partial fraction decomposition. The polynomial breaks apart into distinct blocks. These simplified fractions are no longer abstract numbers. They are the fundamental electrical time constants of the specific resistor-capacitor and resistor-inductor pairings. But we are still in the frequency domain. To process these isolated signals back into reality, we need integration by parts. In signal processing, integration by parts is the mechanical engine operating underneath an inverse Laplace transform. Watch the resulting output. The inverse Laplace transform pulls that signal out of the S-domain and directly back into the physical time domain. By plotting this on an oscilloscope, the engineer sees the exact physical reality of how voltage spikes and decays in the hardware. Without the tandem of partial fractions to break the system apart and integration by parts to process it, engineers would remain trapped in abstract frequency models, unable to verify physical electrical behavior. Moving to the digital domain, these principles suggest a framework for how software architectures handle scale. Conceptually, integration by parts functions as a mathematical mirror to a recursive algorithm or dynamic programming. At its core, integration by parts is simply the exact inverse operation of the differential product rule. We deploy this formula when a system requires integrating the product of two distinct functions that lack a clean chain rule relationship, like x multiplied by e to the x. The technique relies on strategic assignment. You assign one function to be u, the part of the problem that gets simpler when differentiated. The other function becomes dv, the part that is easiest to integrate. To make that strategic choice, mathematicians and computer scientists use a standard heuristic, ILATE. ILATE prioritizes which function type should be assigned to u based on how quickly its mathematical complexity degrades when differentiated. Inverse trigonometric functions degrade the fastest, exponentials degrade the slowest. Look at how this formula structures an operation. It parallels the logic of computational reduction used to resolve complex problems. The algorithm tells the system to strip off one solvable chunk of the problem first. That is your u times v. It then takes the remainder, the slightly less complex integral of v du, and passes it back into the function recursively. The system iterates. Integration by parts operates as a systematic recursive loop. It continuously strips away complexity, step by step, until the entire remaining system resolves down to zero. Understanding the theoretical mechanics of calculus is necessary, but modern engineering requires computational execution. In a live production environment, manually grinding out algebraic coefficients to isolate variables creates a massive bottleneck. A system's architect's time is valuable. Their focus must remain on designing the structural logic of decoupling variables, not performing rote arithmetic on a whiteboard. This IDE interface shows how we automate that heavy lifting today using Python and its SymPy library. Within the script, the engineer defines the complex, entangled rational expression exactly as it exists in the physical model. To execute partial fraction decomposition computationally, we call SymPy's apart function. Watch the output terminal as the code runs. The apart function instantaneously forces the expression apart. The exact mathematical decoupling we previously modeled by hand on the satellite bracket is achieved in milliseconds. With the variables automatically isolated into fundamental fractions, the engineer can write a loop to feed this decoupled output directly into a continuous integration sweep. This computational pipeline bridges theoretical mathematics and applied system modeling. The logic dictates the code, and the code dictates the hardware. Mastering mathematical decoupling, whether conceptualized through the recursive logic of integration by parts or automated via SymPy scripts, gives engineers the ability to resolve overlapping constraints into independent, actionable variables.